Hi there everyone, welcome to another Chem Complete lecture, and we are going to continue talking about kinetics in today's lecture. So just a brief reminder before I get started, head on over to chemcomplete.com and check us out over there. We've got lots of free resources, and I do offer one-on-one private tutoring. It's very affordable. So if you're struggling with chemical kinetics or any other type of material in your chemistry course, why don't you go over there and scope out what we've got, because there's a lot of potential that we could help you. So again, chemcomplete.com, and let's get started with today's lecture. So this lecture is going to be oriented towards determining the order of overall reactions as well as the order for individual pieces of a rate law and how to determine rate constants. So the first thing you want to understand when we talk about a rate law is going to be governed by the following. So we will say that rate is going to be equal to a rate constant, which we use lowercase k to represent, and then it will be some concentration of your reactants. So I just put A and B here as placeholders. Now there are values, we'll call them X and Y for right now, that these can be raised to. Those are different than the stoichiometric values. So if you remember in equilibrium, we take the stoichiometric coefficients and we raise the concentrations to that power. That's not what happens with rate laws. We have to actually experimentally determine these values and decide what gets plugged in there. But X and Y here are going to be referring to what's known as the order of these reactants relative to the reaction. So if something is raised to the 1, that would be considered first order with respect to the reaction. Okay? If something is 2, then it is second order relative to the reaction. 3 would be third order. Okay, so it is also possible that you could have something raised to the 0th order for a reaction, which means that that compound, because anything to the 0th order or anything raised to the 0 is going to come back as 1, that's not going to participate in the reaction. So anything that is the 0th order, it's not, the rate of the reaction will not be dependent on it. That's the way that I should state that. So if you take a look at what we have here, okay, the goal is going to be, number one, how do we determine these order values? Because we can't write a rate law without actually knowing, am I squaring something? Is it going to be cubed? Is it just staying exactly how it is? Does it drop out because it's to the 0th order, etc.? So that's very important. And then second, how do we determine the value of K? So it's a constant. It's going to be unique to each individual reaction, but I want to be able to calculate K if I know the order of the other reactants that are fitting together there, and that will create the rate law. So that's what we're going to attempt to do here today. So here is an example for us to work through so we can see how this works. Right? It says use the information to determine A, the rate law, and B, the rate constant. So this means that we want that whole entire rate equals K. Okay, and in this case, we're going to have NO and H2, and we need to find out what we're raising those to in order to complete the rate law. And then the second question is saying, what is the value of the rate constant that is in that rate law? So what is the numerical value of K? That's what we're going to be trying to solve here. So we're provided with a balanced equation, and we are given some experimental data. So you may be familiar with this. Gone through a lab where you collect this type of experimental data, or you've seen it in a text problem. So we've got 3 experiments here. Now, when we get ready to determine rate laws and rate constants, it is very typical to hold the concentration of one of the reactants steady while you manipulate the other. And you see what that does to the rate. And the reason for that is if we just turn around and say, let's double the concentration of both and see what happens to the rate, and then the rate doubles or the rate quadruples, you don't know which reactant was responsible. Were they equally responsible? Was one of them contributing more than another? Was one of them solely responsible and the other one isn't really participating in increasing the rate at all? So that's why we do these one at a time. We say let's hold one of the concentrations constant and we'll manipulate the other. We'll see what happens to the rate. And when we do that, we have the relative rate ratios. That is how we're going to start determining order. So it's very important you understand what order is, and then we can start taking a look at how we're actually going to attempt to determine it. Okay, so let's start. If we're going to have to find for the nitrous oxide and the hydrogen, we'll just start with the NO. All right, so for A, let's start with the concentration of the NO. Okay, now what you're going to do is you're going to take two of the experimental conditions where these are going to be differing. So if you take a look, we have experiment 1, 2, and 3 here. And for the nitrous oxide, when I take a look at this, I have it held constant with 2 and 3, but it changes with 1 and 2 and with 1 and 3. So let's go ahead and use 1 and 2 in order to calculate this. And the way that we would do that is we would say, I'm going to set rate 2 over rate 1. And look at that ratio. All right, now what I have here, if I take a look at it, is the rate for 1 is going to be 1.3 times 10 to the negative fifth, and the rate, okay, for, we're looking right here, the rate for 1 is going to be 1.3 times 10 to the negative fifth, and the rate for 2 is going to be 5 times 10 to the negative fifth. So those values are associated with experiment 1 and 2 where I'm getting a variation in the concentration. So I just want to make sure everybody knows exactly where these numbers are being pulled from. All right, so what I have is rate 2 was 5.0 times 10 to the minus fifth, and then rate 1, okay, was 1.3 times 10 to the minus fifth. And the units here, you can see from the table, is molarity per second. All right, so what does that give me? It gives me the general ratio of rate 2 to rate 1. And what I get here is approximately 4. So what that says is that the rate in experiment 2 was 4 times faster than the rate in experiment 1. So this is the relative rate ratio in these differences here. Now, when I have this, this is not the answer itself. I'm not going to raise the NO to the 4th power. What I want to do now is set this equal to those concentrations in order to determine this. All right, so you're going to have to follow along here. The way that I do this is I can say rate 2 over rate 1 is going to be equal to, now I turn around and I can set them equal to the actual rate laws. So I can say it's going to be K, all right, and K. So these are the rate constants for 2 and 1 here. Okay, and that's going to be the concentration of the NO. So the concentration in experiment 2 was 10 times 10 to the negative third. So I'll go ahead and I'll put that in there. 10 times 10 to the negative third. Okay, and this is going to be raised to the x. That's what I want to figure out, the order, right? And then this is going to be 5 times 10 to the negative 3. Okay, these are the concentration values, and that's x there. All right, now I would also have the concentration of H2 raised to the y, and H2 raised to the y, and we'll figure that out later. But the key here is that H2 didn't change when we went through experiment 1 and 2. So I don't need to worry about this at this point, and I also don't need to worry about the rate constants right here. So I'm looking at the relative ratio in the rates compared to the ratio of the concentrations, and that's going to be what allows me to solve for x, right? So this little chunk right here, if I solve for that, I find that that is going to equal 2x, right, 2 to the x. And we said before that rate 2 over rate 1 is equal to 4. So 2 raised to the x is equal to 4. Well, now it's very clear that x is 2 when I solve this. So there is the order. That means that when I solve for the rate law, I need to take NO squared. It's going to be second order relative to this reaction. So this is how you determine this experimentally. Now the next thing that we're going to go and tackle is we want to find it for H2, because we have two reactants here when we get ready to do the rate law, and we need to solve for both of them. So when we get ready to do H2, all right, we can come up here and we can take a look. Now, the differentiation in this case is going to be between experiment, we have 1 and 2, it's being held constant, but experiment 1 and 3, there's a differentiation, or 2 and 3. So you can take your pick there as you're working with it. So in this case, let's go ahead and do H2, and we'll do experiment 3 and experiment 2. So we'll do rate 3 and rate 2, okay, and set those equal to one another. So in this case, we're going to say I have rate, and let's just mention this is for H2 here, so we don't confuse ourselves, right? Okay, so I have rate 3 over rate 2, and this is going to equal 10 times 10 to the negative 5th over 5 times 10 to the negative 5th. So again, these rates are coming from the table up there. I've got molarity second, molarity second. All right, so if I take a look at this, this equals 2, whereas the other one equaled 4, right? So now what I can do is that same technique. I can say that rate 3 and rate 2 is going to equal, and now this time I'm going to drop the K's out and I'm going to drop the nitrous oxide out because that's being held constant between experiment 3 and 2, right? So here's experiment 3 and experiment 2. And if I take a look there, the NO is constant, and the rates here, these are the two that I just used, right? So here are the values that I'm going to use for H2. Okay, everything else dropping out. So for 3, I've got 4 times 10 to the minus third, and for 2, I've got 2 times 10 to the minus third. So you can already see that ratio where it's going there, right? But we'll formally put it in. It's going to be 4 times 10 to the minus third. Okay, and remember that's going to be raised to the y. And then we've got 2 times 10 to the minus third. It's going to be raised to the y. So what does this equal? Well, if I go ahead and I combine that, divide through, I end up with 2 to the y is going to equal 2. So y must equal 1 in that case. So now I've got something that is on the first order for this reaction. So I just leave it as H2. So now I can answer the question for A, which is what was the rate law? The rate law is going to be the rate set equal to my rate constant with the concentration of nitrous oxide squared times the concentration of H2 gas. So there you go. That is the rate law now that we have the orders set. Now if we have the orders set, we can very easily determine what K would be. Right? So in order to find K, all we have to do is rearrange this and then pick out one of our experiments. So what we do is we say to get K by itself, I have to divide through by the concentrations. So the constant is going to be equal to the rate for one of the experiments over the concentrations for those experiments where the concentration of the nitrous oxide is squared and the concentration of the hydrogen is as it is. Okay, so let's go ahead, we'll go middle of the road and pick experiment 2 in order to fill in here. So for experiment 2, if I come up and I take a look, the values that I'm going to need, the rate that will be in the numerator is 5 times 10 to the minus 5, and here are the concentrations. The NO will be 10 times 10 to the minus 3, and the H2 gas will be 2 times 10 to the minus 3. So let's go fill that in. All right, so this is for experiment 2. And again, because this is a constant, unless the temperature is changing between the experiments, this should not have any change. You should be able to do this with all of these. So what I would do here is I would say the rate was 5.0 times 10 to the minus 5 molarity per second. Okay, and then the value down here, I've got 10 times 10 to the minus third molarity, and that is squared. and then I've got 2 times 10 to the minus third molarity, and that just stays as it is. No exponential multiplier there. Okay, so you put all of this together, and if you plug that into your calculator, which I would encourage you to do, you're going to find that the rate constant is equal to 2.5 times 10 to the second, and the value on that is per molarity squared second. All right, now where does that come from? Well, you've got the molarities on the bottom. So if you take a look, you've got molarity squared and molarity, which is going to be a molarity to the third. There's one of them in the top, so molarity to the third drops out to become molarity to the second, and this second in the denominator here matches up with the molarity squared. So that would be the unit on this particular reaction. All right, now it is interesting because the rate constant can have different units. It's going to depend on the order for your reaction, because if this molarity was not squared down here and it was just molarity times molarity, then it would be molarity squared overall. One of these would drop out to give just molarity, and then your unit becomes per molarity second instead of per molarity squared second. Okay, so just keep in mind that the K, the rate constant unit, the value, can change depending on the overall order of your reaction. And when we talk about overall order, we're talking about you need to look at all of the orders for the individual reactants. So for instance, what we have here, you've got the second order for the NO and the first order for the H2. So when we multiply exponents, we add them. And so it is second order with respect to NO, first order with respect to H2. 2 plus 1 is going to be 3. So this overall order for the reaction is going to be third order. All right, and that is where we are going to wrap this lecture up. So if you found this helpful, as always, a like would be greatly appreciated to boost us in the YouTube algorithm. So hit the like button and we can continue bringing this type of content to you. If you comment, we'll do our best to get back to you as soon as possible and engage with the audience. And as always, we greatly thank you for choosing Chem Complete for your lecture needs and spending time focusing on our lecture today. So subscriptions, if you aren't subscribed, go ahead and hit subscribe, because we will be delivering content throughout your semester. We want to make sure you're up to date with everything as it's coming out. And I do field questions in the comments and create videos based on that. So if you have an idea for a video or you would like to see something addressed that's not currently on the channel, you never know, I might be able to make a video for it. So we encourage you to engage here. Again, one more shout out to chemcomplete.com. You can check us out over there. We've got one-on-one tutoring, very affordable for college students, and we also have lots of free resources that are continuing to expand every month. So thank you for your attention and choosing us as your learning resource. I will see everybody for the next lecture.